All right, so now we're going to take a look at sampling distributions, okay? And what we're going to do is we're going to collect a sample from a population. There's an underlying parameter for my population. In this case, I want to take a look at the population mean, mu. So underlying a population, the population, if you collect every single element of the population, every single member of the population, and you calculate the arithmetic mean for the entire population, you'll get mu. We use X bar to estimate mu. So instead of going out and doing a census of the entire population, we collect a sample of size n, which size n, lowercase n, would be smaller than the size of the actual population. So let's say I have a population with, I don't know, 300,000 members, and I want to take a sample of size 100. So I take a sample of size 100, okay? And I calculate the mean for that sample. That mean will be X bar. X bar is my estimate for mu, the population mean, but it's the sample mean of only the 100, okay? And it's not necessarily going to give me exactly the population mean. As a matter of fact, my first X bar is short of the population mean. It's less than the population mean. It's smaller, okay? I can go out and I can collect another sample of the same size, size 100, and calculate the mean for that one. I won't get the same number. I'll get another X bar most likely. And that X bar may be closer to the population mean, it may be further, but it's another number that I'm assuming is close to the population mean. And I can continue to do this. I can collect another sample. Maybe that one overestimates the mean, is bigger than the mean. And then I can continue to do this, another sample of size 100. So I have a fourth sample of size 100 and collect another one and another and another. And I just keep collecting samples of size 100. As I continue to do this, what's going to happen is as long as I collect either a large enough sample, which roughly is greater than 30, any sample greater than 30 we consider to be large enough roughly, or the original underlying population is normal. If any one of those two things is true, as I continue to collect sample means, what happens is those sample means are also normally distributed. So when I collect all these sample means from samples of size 100, as long as the original population is normally distributed, or the sample size is large enough, as I continue to collect those sample means will have a distribution that's roughly normal. And the other thing is the mean of all those sample means. So if you were to take all these sample means and calculate the arithmetic mean for all of these X bars, so you add up all of the X bars and you divide them by the total number of samples that we have here, then that mean of all those X bars will target the population mean, will be exactly the population mean. All right, so let's take a look at an example. I have here a population. My population only has 3 members. There are only 3 things. So capital N, the population size is 3, okay? Let's say this represents the tenure at my company for my 3 employees. I only have 3 employees. I have a small company, and one of my employees has been there for 18 years, one has been there for 12, and the newest guy has only been there for 4. So I have 3 tenures there. Um, that's the entire population for my company. What I'm going to do, I'm going to go ahead and calculate the population mean to calculate on average how long my employees have been employed by me. All right, so to calculate the population average, I'm going to go ahead and add up all the elements of my population, add up all the values 4 plus 12 plus 18 to get 34, and I'm going to divide that by 3 because I have 3 employees, and the arithmetic mean is going to be 11 and a third, or 34 over 3. So that's 11 and a third is the average amount of time that my workers have been with me. 34 over 3, which is when you approximate, well, it's actually exactly 11.3 repeating. So 11 and a third years is the average amount of time that people have been with my company. All right. I can also calculate the standard deviation. So the standard deviation here, or not, sorry, not the standard deviation, the variance. The variance is a measure of spread, a measure of variation. It tells you how far apart the individual values are on average. And here is the variance. So to find the variance, I'm going to take each value, 4, 12, and 18. I'm going to subtract mu, which is 34 over 3. So each value, 12, 4, 12, and 18. I subtract mu, 34 over 3 from each one. I square the results, and I take that sum, add them all up, and divide by 3. I get 296 over 9 for the population variance. So I've calculated the population mean, mu, and the population variance, sigma squared, from my population of 3 workers here. All right, so now I'm going to take a look at taking samples of size 2. So my population size is 3. My population size is 3. I'm going to look now at taking samples, or lowercase n, samples of size 2. So I'm going to look at every possible sample of size 2, and I'm going to do this with replacement. So every time I select a value from my population, I'm going to replace that value so that it can be selected a second time possibly. Okay, I'm going to do it with replacement so that the trials or my samples are independent of each other. Okay, that's the reason I'm doing it with replacement, so I can have independent samples. All right, so one sample could be 4, 4. I could reach in and pull out a 4, then reach back in a second time and pull out another 4. That would be my first sample of size 2. Another sample of size 2 would be 4, 12. Reach in first and pull out a 4, then second I pull out a 12. Or 4, 18. Those are all the possible samples where I reach in first and pull out a 4. Okay? Then I could reach in first and pull out a 12. I could get a 12 and then a 4, a 12 and then a 12, a 12 and then an 18. Okay, so those are all the samples where I reach in and first pull out a 12. And I'm going to do the same thing with 18. So I reach in first and get an 18, or 18, 4, 18, 12, or it could be an 18 and an 18. Okay, so once I have all of that, those are all my possible samples of size 2. That's every single possible sample of size 2. What I'm going to do is I'm going to calculate the sample mean from each one, x bar. So I'm going to calculate x bar. I've already calculated the population mean mu, but now I'm going to calculate the sample mean for each of these individual samples. So 4 plus 4 is 8. 8 divided by 2 is 4. So I'm going to just find the arithmetic mean for each sample. 4 plus 12 is 16. 16 divided by 2 is 8. 4 plus 18 is 22. 22 divided by 2 is 11. And then I continue in that fashion, calculating all the sample means. So those are all the sample means, okay? Then I move on. What I'm going to do now is I'm going to create a probability distribution for my sample means. So you see here I have 1, 2, 3, 4, 5, 6 possible sample means. I could get a sample mean of 4, a sample mean of 8, 8 occurs twice, a sample mean of 11, 11 occurs twice, a sample mean of 12, a sample mean of 15, which also occurs twice, or a sample mean of 18. Those are all the possible sample means for samples of size 2 from this population. So I'm going to use my sample mean as my random variable. So my random variable is my sample mean. Here is every single possible value for my sample mean. So this is a list of all the possible values of my random variable. And over here I have the probability of getting each of these individual values. So the probability of getting a sample mean of 4. Well, 4 is only one of the total possibilities, so there's 9 possibilities. 4 is 1/9 of the probability. A sample mean of 8. The probability of getting an 8 is 2 out of 9, 2/9, so 2 out of 9. Probability of getting an 11 is also 2 out of 9, 2 11s out of the total 9 possible sample means. Probability of getting a 12 is 1/9, 15 is 2/9, because there's two 15s, and the probability of getting a sample mean of 18 is 1/9. So this is my random variable x bar, and these are the probabilities for each of the values of my random variable. I have here a probability distribution for the random variable sample mean. Sample mean is my random variable. This is what we call a sampling distribution. It's when you create a probability distribution based on some sample statistic like x bar or p hat or s squared, this sample standard deviation. If you create a probability distribution based on a sample statistic, that is what we call a sampling distribution. Okay, so remember, it comes from sampling a bunch of times, taking a bunch of different samples. We have here every possible sample. All right, so here are some things that we need to look at when it comes to uh, the sampling distribution. Um, First, if you have a sampling distribution, one thing you can do here is you can go through and you can calculate the mean of this probability distribution by taking each of the values of the random variable, multiplying it by its corresponding probability, and then summing them all up. So this is how we calculate the mean of a probability distribution. I'm going to do that for my sampling distribution. So here we go. So for my sampling distribution then, what I'm going to do is I'm going to multiply in this next column. Actually, let me make a straight line here. In the next column, I'm going to calculate x bar times p of x bar. I'm just going to multiply x bar by the p of x bar. So x bar multiplied by p of x bar. And in doing this, let's see, 4 times 1/9 is 4/9. 8 times 2/9 is 16/9. 11 times 2/9 is 22/9. 12 times 1/9 is 12/9. Oops. 12/9. And 15 times 2/9 is 30/9. And 18 times 1/9 is 18/9. 18/9. So what you want to do is you want to add all of them up, right? It's the sum. So adding these all up, 4 plus 20, 4 plus 16 is 20, plus 22 is 42, and then 56 plus 30, 86 plus 18. And here I get 102 over 9, which I simplify 102 over 9 by dividing the top and bottom by 3. I get 34 over 3. So it turns out that the mean for this sampling distribution is equal to 34 over 3, and that's actually the population mean. So the sampling distribution mean turned out to be the population mean. All right? Okay. So I have the sampling distribution mean, mu of x bar, the mean of the x bars, that's the sampling distribution mean, is equal to the population mean. Okay? All right, so let's go ahead and let's actually calculate another thing. Let's calculate the variance of this sampling distribution. So to calculate the variance of the sampling distribution, oops, once again, let me make a straight line here. To calculate the variance of the sampling distribution, what I'm going to need is I'm going to need to calculate the x bar squared, square the x bars, multiplied by p of x, multiplied by p of x bar actually, multiplied by p of x bar, and I'm going to need to add all of those up. So x bar squared multiplied by p of x bar, and I'm going to add all of those up and then subtract the mean squared, subtract mu squared. So let's go ahead and do that. All right, so 4 squared is 16. 16 times 1/9 is 16/9. 8 squared is 64. 64 times 2/9 is 128/9. 128 over 9. 11 squared is 121. 121 times 2 is 242/9. 242/9. 12 squared is 144. 144 times 1/9 is 144 ninths. 15 times 2 is 225. 225 times 2/9 is 450 ninths. And 18 squared is 324. 324 times 1/9 is 324 ninths. So this is my x squared times p of, or x bar squared times p of x bar. Um, I need to add all of those up. When I add all of those up, what I get is 1304 over 9. So I get 1304 over 9. When I add up all of the x bar squareds times x bar, what I'm going to do is I'm going to have to subtract from that mu squared. Remember, mu was 34 over 3, so I'm going to need to subtract from that 34 over 3 squared. And what we get there, after doing all that calculation, is we get 148 over 9. 148 over 9 after doing that calculation. So the variance of this sampling distribution is 148 over 9. Here we go. That means that sigma squared of x bar is 148 over 9. Now let's compare these. It turns out that this number that I found for the population variance, 296 over 9, is related to this number, the sampling distribution variance. The sampling distribution of x bar, when I calculate the variance, what I get is I actually get the population standard deviation, or sorry, the population variance, sigma squared. I get that divided by n, okay? Because that's exactly what this is. If I take 296 over 9 and I divide it by n, which is the sample size. Remember, all my samples were size 2, right? And if I calculate this, I will get 296 over 9 multiplied by, I'm going to divide by a fraction, so I multiply by its reciprocal, multiplied by 1/2, and that's where I get the 148 over 9. So it turns out that when you're dealing with the sampling distribution mean is equal to the population mean, and the sampling distribution variance is equal to, sorry, the population variance is equal to the sampling distribution variance is equal to the population variance over n. So this is why the sampling distribution is significant. And once again, this is as long as n is greater than 30 and or your original population is normally distributed.